And well, we have another problem at the screen, and the statement of the problem is a cube is given a velocity v0 upward along the surface of a smooth wedge located on a smooth horizontal table, no friction. The angle at the base of the wedge is alpha, and the masses of the cube and the wedge are the same. Okay. And after what time will the cube return to its original position on the surface of the wedge? And also find the velocity of the cube at this moment. And this is the problem. And we need to solve it. I guess wedge was initially at rest. It should be. Otherwise, its velocity should have been mentioned. So initially only the cube is given the velocity v0, not the wedge. Wedge will gain the velocity because but initially it was as at rest. I'm considering it, I'm insisting on it. So can we consider the motion of the system center of mass? Because I can see one thing here, that since external forces act only vertically, so horizontal component of the center of mass velocity remains constant. I guess so. The external forces on the system is only gravity and the normal force exerted by the table, and both are in vertical direction. So no external forces for the system. System means wedge and the cube. So no external forces in horizontal direction. That means horizontal component of the center of mass velocity remains constant. And it is equal to what? जो इनिशियली था वही हमेशा रहेगा, because its horizontal component of center of mass velocity is constant. So horizontal component of center of mass, initially the block was given some velocity v0. So velocity, to find the velocity of center of mass in horizontal direction, I am describing everything along the horizontal right now. BCM equal to m1 v1 plus m2 v2 divided by m1 plus m2. And since m is same for both of the objects we are discussing here, so BCM simply becomes b1 plus b2 by 2, and that means v1 is the velocity of let us consider v1 be the velocity of the cube. At the initial moment, velocity of the cube in horizontal direction is v0 cos alpha, and wedge was at rest. That means VCM is half v0 cos alpha VCM, and it is going to remain constant, remain the same for whole journey. That's right. And now what? By the time cube returns to the starting point of the wedge, कैसे हुआ होगा? How? I don't know. I don't want to know. But क्या हुआ होगा? I can only guess. You can see the picture here. I have taken an arbitrary direction x. वो मेरी मर्जी पर है, वो प्रॉब्लम सॉल्व करने के चोचले हैं सारे. बट यू कैन सी कि हुआ होगा फाइनली यही. शुरू में तो मामला यही था. यू कैन सी हियर कि शुरू में सारा मामला कुछ ऐसे था, और थोड़ी देर के बाद आ ही गया होगा. ये जहाँ था वहाँ यहाँ पर पहुँच गया, तो उस टाइम तक वेज कुछ न कुछ आगे मूव कर गया होगा. वेज का अपना मोशन एक्सेलरेटेड होगा. सेंटर ऑफ मास ऑफ द सिस्टम इज मूविंग विद कांस्टेंट वेलोसिटी. बट वेज को भी एक्सेलरेशन होगा और उसको भी एक्सेलरेशन होगा, दोनों को. So I'm playing with the fire, and this angle is always alpha. Okay, fine. Now what can I do? What can I think? Let's remove all those things I have drawn and think freshly. I can see the block displacement is S. The block's displacement is S, and it is horizontal, no doubt at all. It is horizontal, and displacement is horizontal. And blocks means the cube's displacement is S, and it is horizontal. And so will be the displacement of the wedge, क्योंकि वेज ने भी उतना ही डिस्प्लेस किया होगा सर्टेनली, क्योंकि वहीं पर आके गिरा है वो क्यूब. सो हॉरिजॉन्टल डायरेक्शन में ब्लॉक का भी डिस्प्लेसमेंट हॉरिजॉन्टल डायरेक्शन में ही डिस्प्लेसमेंट है फाइनली क्यूब का और वेज का, दोनों के डिस्प्लेसमेंट सेम है. So will be the displacement of the center of mass, because we know that displacement of center of mass is displacement of wedge plus displacement of cube divided by 2, and since these two are same, so upper thing becomes simply 2s by 2. So S is the displacement of both block and the wedge. So I'm going to make a statement here. By the time t of the cube's return to its starting point on the wedge, the displacement S of the center of mass will be equal to the displacement of the wedge and the cube. And this is my statement. I got it. And now what is this displacement exactly? Because I can find out the magnitude of displacement as well, because I know the velocity of the center of mass. So I have related both the displacements of the cube and the wedge to the displacement of the center of mass, because I know the velocity of the center of mass and it's going to remain constant. And so the displacement can be written as half V naught cos alpha multiplied by t. T is the time after which the cube returns to the wedge. So this is it. This is my equation number 1. And I need to find this time as required by the problem. And I know I'm not going to use Newton's laws, putting lots of observer and many more things. My observer is well on the ground, and I don't want to get into a trap. So I'm going to think simply. Initial velocity was this, and I'm an observer at the ground, so I can see here the forces acting on it. This is normal and this is the wet at this moment, and I'm thinking the initial moment. So this is mg sine alpha and this is mg cos alpha. I had to write these things, and these forces will continue to act on it. Well, normal can change, but mg cos alpha and mg sin alpha is not going to change. So its velocity can change. But if I take this x-axis independently, not related to anybody in a space, then I know its initial velocity is along the x-axis and its acceleration mg cos alpha, though mg cos alpha, not acceleration exactly, the force component mg cos alpha is the only thing acting on it along the x-axis. Of course it is along the negative x-axis, but ये हमेशा लग रहा है mg sin alpha इस पर हमेशा इसी डायरेक्शन में लगेगा और ये अकेला फोर्स होगा हमेशा उस डायरेक्शन में. So I got the initial velocity, I got the acceleration, that is g sin alpha in this direction, and initial velocity v0 in this direction, and this g sin alpha can be forever. That means I can find out the x component of this velocity. X is not horizontal. Here is another x-axis, as you can see on the screen. So I can always find the x component of its velocity or x component of its displacement. Displacement is strictly not along x-axis, but I can find the x component of its displacement is horizontal basically, but I can find based on Newton's second law of motion, that the acceleration of the cube along my fixed x-axis parallel to the surface of the wedge, and it has nothing to do with the wedge motion. The observer is sitting on the ground, and for this observer the acceleration of the wedge along the x-axis is minus g sin alpha. Minus sign because it is opposite to the direction, positive direction of x-axis. It is towards the negative x-axis. So I could write this displacement x1, and x1 will be equal to उसी डायरेक्शन में वेलोसिटी मुझे पता है, and it gave me the strength to work like that. ut v naught t minus half g sin alpha is the acceleration there, multiplied by t square. So this is my equation number 2, and x1 is simply s cos alpha. S cos alpha, the net displacement of the cube. x1 is just a component, so we can write x1 equals s cos alpha. And if I can relate both of them, that means s I can write half v naught cos alpha t, and multiplied by cos alpha, so it becomes cos square alpha. That is x1, that it becomes x1, and I can equate it with another x1 I wrote, v naught t minus half g sin alpha t square. Then I can get the value of t. Of course I can get the value of t, and I got it already. I got the t equals v naught 1 plus sin square alpha by g sin alpha, and the time I got. Now it's time to find out the velocity of the cube when at the moment of its return to the starting point on the wedge. So how can we do this? In horizontal direction, I know velocity of the center of mass is in horizontal direction and it's a constant. And in the horizontal direction, both the cube and the wedge both have same displacement. That means in horizontal direction, velocity of cube and velocity of wedge are same, because VCM can be always written as VC plus VW by 2. If these are not same, VC and VW are not same, which are, then all three values will not be the same. So VCM is definitely equal to VC and VW in horizontal direction. This is all horizontal direction considerations. So I would like to invite the principle of superposition of velocities, and I can write velocity of cube equals velocity of cube with respect to wedge plus velocity of wedge. And in horizontal direction, velocity of cube and velocity of wedge is same, so VCW equals 0. So it's come out nothing. If I can put 0, that means VC equals VW, and I got nothing. That means what? That means the velocity, I can get one thing more. I can get the velocity x component of the velocity of the wedge at the moment, because I knew the displacement and the time. So, and the acceleration and the initial velocity. So I can write here v equals u plus at. So x component of the velocity at the moment of its return to the starting point on the wedge, the velocity x component of the velocity is x, vx, and x-axis is the same. You can see here, this is, and I can write vx equals v naught minus g sine alpha t, and t is here, and I put those values. I can get v naught minus g sine alpha t is v naught 1 plus sine square alpha upon g sine alpha. So it gets cancelled out, and I can see here this value is simply v naught sine square alpha. So I get the velocity of the cube along the x-axis like this, v naught sine square alpha, and I guess this is vertical and this is horizontal, and this angle is alpha and this angle is 90 minus alpha. And x component, yes. What about the horizontal component of the velocity of wedge? It will have something, but the wedge has got no velocity in vertical direction. So if I use the principle of superposition, I can write velocity of cube equals velocity of cube with respect to wedge plus velocity of wedge in vertical direction. Then velocity of wedge is 0, and velocity of cube is equal to velocity of cube with respect to wedge, but I don't know the velocity of wedge. That means velocity of cube at the moment is in vertical direction. in this direction. So its component along this is v naught cos v naught. If this velocity of cube along the is along the vertical at the moment, I got it. I don't have to think anything like this, not even the principle of superposition or anything else. Oh, what I was missing. I got the x component of the velocity as v naught sine square alpha. So it will have a velocity in this direction. And if I got, of course, this angle is alpha and this angle is pi by 2 minus alpha. And if I think the velocity of the cube at the moment it returns to the starting point on the wedge is v naught sine alpha in vertical direction, then its x component is going to be v naught sine square alpha only. So this is the velocity. I can guess it, and this is the answer. That velocity of the wedge at the moment of returning to its initial height, the speed of the cube is directed, the velocity of the cube is directed vertically downwards, and it is equal to v naught sine alpha. I guessed it right, and this could be the answer, because principle of superposition of motion is taking me to find out the velocity of wedge and many more things. But look, I'm sorry, I wasn't trapped in the change of frame. It simply came out by sitting on the ground only. Thank you very much for watching.